All right, this is Chapter 5, Section 5, Theorems about roots of polynomial equations. Please fill in your name, my name, the class that this is, the date, and your learning objective is to solve equations using the rational root theorem and to use the conjugate root theorem. The rational root theorem, we're just going to dive in. So let's say you have a polynomial with integer coefficients. We know that there are a limited number of roots where our polynomial is equal to 0. So I'm going to highlight what I want you guys to write down. Let's get my highlighter out. So I definitely want you to write rational root theorem. I want you to write integer roots must be factors of a sub 0. And a sub 0 in layman terms is the constant term. Or the last number. The one without a variable on it. Okay. And rational roots must have reduced form of p over q, where p is an integer factor of a sub 0, which is that constant term again, and q is an integer factor of a sub n. And remember, a sub n is the leading coefficient, or the first coefficient of the first term. Okay, so we have a little example here. The last term is 10, and the first term is 21. So you're going to list all the factors of 10, and in this case, we are considering the positive and negative factors. So -1 and -10 will give you positive 10. +1 and +10 will multiply and give you 10. So we're going to list both of the positive and negative versions of each factor. So the factors of 10 are 1, 2, 5, and 10, and we have the positive and the negative version of each one of those. Okay, you look at your leading coefficient, it's 21. So you list all the factors of 21. Now, the root of this polynomial is going to be a combination of p values, which is this guy, over q values, which are these guys. And then you can confirm by graphing, or in this case, they divided everything by 21 and factored. You can confirm that the roots, or the zeros of this function, are 2/3, which 2 comes from here, 3 comes from here, and -5/7. The 5 is from here, and the 7 is from here. So we're going to find factors and then get a list of possible rational roots. So let's see another sample of that. So when we're finding a rational root, the only possible rational roots have the form of, it's going to be a factor of our constant term, which in this case is -8, and a factor of our leading term, which over here is 3. So we're going to list all of our factors of -8, and I know plus or minus 1, 2 is a factor of 8, 3 is not, 4 is a factor of 8, 5 is not, 6 is not, 7 is not, and 8 is a factor of 8. So all the factors of -8 are 1, 2, 4, and 8, and the positive inversions, negative versions of those. Okay, so now I'm going to list all the factors of 3. Thankfully, there are 3 is a prime number, so there are only 2 factors for 3. And now the possibilities are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1, and then the same possibilities, plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 4 over 3, and plus or minus 8 over 3. These simplify down. Let's list them in largest to smallest. Negative 8 is going to be my smallest. Boop. Then we got negative 4. Then we have 3 goes into 8. So negative 8/3. Then we have negative 2. We have negative 4/3. Boom, we've used that. Negative 2/3, did use that. We have negative 1. And then we have negative 2/3. This is just a fun activity with fractions. Negative 1/3. And then we start our positives again. So then we'll have positive 1/3, positive 2/3, positive 1, positive 4/3, positive 2, positive 8/3, positive 4, and positive 8. So we're going to do a little test. There are at most 3 of these that will work. Some of them may not work. So I'm going to use a graphing utility to help me find this. And I'm just going to pull in Desmos. Okay, so I'm going to show you how to use Desmos to find the values quickly. You can do this with Excel. You can do this with your TI-83, your graphing calculator. It's pretty quick and easy. So let's take, we're going to go ahead and put our zeros in for x. So we think it's negative 8. We think it's negative 4. Negative 8/3, negative 2, negative 4/3, negative 1, negative 2/3, negative 1/3, 1/3, 2/3. 1 4/3, 2 8/3, 4, and 8. So then we look at our table and we find the ones that are zeros. Oh, it's here. It's at 2/3. So let's go ahead and snip this as our evidence. So make sure you include the table. That's why Desmos is lovely. Take that snip, and then we have that evidence. That 2/3 is the rational root. So because 2/3 is the 0, that makes this one the root. All right, so let's take a look at when we want to find the roots, and not just one, but any and all. So once we find one root, we can use synthetic division to factor the polynomial. We can continue finding roots and dividing until I have a second degree polynomial that's like an x squared. And then we're going to use quadratic formula to find remaining roots. So let's go ahead and circle what we use. So we are going to find one root. So step 1. Step 2 is use synthetic division to factor the polynomial. And then we are going to continue that process until we have a second degree. And then we're going to use quadratic formula to find the remaining roots. So let's apply that here. So we're going to take a look at our constant term, which is -6. So we got plus minus 1, plus minus 2, plus minus 3, plus minus 6. All these guys are factors of -6. And then we're going to take our coefficient, our leading coefficient, and find its roots, thankfully. 2 only has 2 roots. So we're going to put together a list of possible rational roots. So it could be plus or minus 1. So I'm going to go 1, 2, 3, and 6 all over 1. Because remember, it's the last one over the first one. So these are all the ones divided by 1. I'm going ahead and simplifying. 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, and 6 over 1 is 6. Now I'm going to do 1 over 2 is 1/2. That's 1/2. 2 over 2 is plus or minus 1, which I already have. 3 over 2. This is going to show up as 1.5 if we do it in our graphing utility. And then plus or minus 6 over 2. 6 over 2 is 3. And so I already have that one here. So we're going to go ahead and list these. We're going to make a little table like we did in Desmos. All right, so when we put that in Desmos and we test each of these roots, we find that -3/2 is our 0. So what we're going to do is we are going to use synthetic division to find, to factor this polynomial. So it would be 2, 1, -7, -6. So we bring down the 2. -3/2 times 2 is -3. 1 plus -3 is -2. -3/2 times -2 is +3. -7 plus 3 is -4. -3/2 times -4 is +6. If you don't believe me, go ahead, try it. Do out the math. And so my first root is x plus 3/2. It's always opposite of what the root is. And then the other factor is 2x squared minus 2x minus 4. And then we can use quadratic formula. So this is the scenario where we have a second degree polynomial and we can use quadratic formula. I'm actually going to factor out a 2. Minus x minus 2 I'm sorry. I was looking for 1, and I can see I have more than 1. If I divide both sides by 2, it gets rid of this 2 here. Go ahead and factor this. Two numbers that multiply to give me -2 and add to give me -1 is -2 and +1. And then, as you guys can see, I did not add the 1. Good thing I factored it out. I didn't test -1. It's here, but I didn't test it. Here. So give me a second. Let me pull the -1 and. Okay, so when we test 1 and -1, we see that -1 is also a 0. So when it's asked what are the rational roots of this number, we can find, if we can locate the first one, then we can use synthetic division and end up finding the rest of them. So my official roots are x equals -3/2, x equals 2, and x equals -1. All rational, all roots. All right, we're going to take a look at the conjugate root theorem. So we're going to actually use this theorem to deal with when we have complex roots. So if f of x is a polynomial with rational coefficients, then irrational roots of p of x equals 0 that have the form a plus root b occur in conjugate pairs. So if a plus the square root of b is an irrational root, then a minus the square root of b is also a root. So that's what I want you to write in your notes. The conjugate root theorem, and that if a plus root b is a root, then a minus square root of b is also a root. And that works for complex roots as well. If a plus bi is a complex root, then a minus bi is also a root. So we just need one to be able to determine the other. So let's look at this example problem. A cubic polynomial has real coefficients. 3 minus 2i and 5/2 are two roots of our polynomial. What is one additional root? So we're going to look at the complex one, and we are going to write, so this one is 3 minus 2i, the one with the opposite sign in the middle is going to be also a root. So an additional root is 3 plus 2i. Both of these guys are roots. Done. All right, so that, I know that seems too easy. It's just that simple. Here's where it gets a little bit difficult. What quartic polynomial equation has the roots 2 minus 3i, 8, and 2? So using the root theorem, we know that x minus 2 minus 3i times x minus 8 times x minus 2. And we can say, because this is a complex root, that 2 plus 3i is also a root. So we have to include that as well. So we get x minus 2 plus 3i. So now I have 4 x's. We're trying to make a quartic, so I've got all the pieces I need to make the equation a quartic. So now it's just a bunch of multiplying. So the first thing I'm going to do is distribute out this negative. So I get x minus 2 minus 3i. And I'm going to distribute out this negative here. X minus 2 plus 3i I'm going to go ahead and multiply these guys out. X squared minus 2x minus 8x plus 16. All right, so this is a 3-term item that's being multiplied by another 3-term item. So just keep track. Everything's going to get multiplied by x in here. So it's going to be x squared. Let me get a different color. So x times x is x squared. X times negative 2 is negative 2x. X times 3i is plus 3ix. Then everything's going to get multiplied by negative 2. X times negative 2 is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times 3i is negative 6i. And everything's going to get multiplied by negative 3i. Negative 3i times x is negative 3ix. Negative 3i times negative 2 is positive 6i. Negative 3i times 3i is negative 9i squared. All this, y'all. What? Okay, so we got x squared. These guys combine together, negative 10x and plus 16. Okay, so now I have to combine like terms. I thankfully only have one x squared term, so he's going to enter. I'm going to cross them off after I have checked to see if there's any like terms. Negative 2x minus another 2x is negative 4x. Positive 3ix and negative 3ix are 0. Then I have a positive 4. Negative 6i plus 6i is 0. And minus 9i squared. I squared is equal to negative 1. That's going to multiply by x squared minus 10x plus 16. Okay. Next, I have to simplify this term here. X squared minus 4x plus 4. Negative 9 times negative 1 is positive 9. I'll rewrite that guy. 4 plus 9 is 13. So x squared minus 4x plus 13 times x squared minus 10x plus 16. Now everything, we're going to multiply again. I know, tons of multiplying. So x squared times x squared is x to the 4th. X squared times negative 10 is negative 10x squared. X squared times 16 is 16x squared. Negative 4x times x squared is negative 4x to the 3rd. Negative 4x times negative 10 is positive 40x. And negative 4x times 16 is negative 64x. Then it's 13's turn. 13 times x squared is 13x squared. 13 times negative 10. Oh, fudge. Okay. Negative 10x. I'm just going to double check that x squared, that's x to the 3rd. 40x squared. And 10x is... Okay. So 13 times x squared is 13x squared. 13 times negative 10x is negative 130x. And 13 times 16, oh, I'm going to have to get my calculator for that. 13 times 16, 208. Okay, I know it seems like a lot, but let's just Simplify, simplify, simplify. Okay. X to the fourth doesn't have any x to the fourth to combine with, so he is done. X cubes, negative 10x cubed, minus 4 more x cubes is negative 14x cubes. Once I use them, I'm going to cross them right off my list. X squareds are here. 16 and 40 add to give us 56, plus 13 is 69. Boop, boop. Negative 40. Okay. X, negative 64 minus 130 is negative 194x plus 208. Check and check. So x to the fourth minus 14x cubed plus 69x squared minus 194x plus 208 is a quartic polynomial that has these roots. Woo! Sorry. Okay, last one, guys. Promise. Last one. Descartes' rule of signs. Descartes' rule of signs. Okay, so what Descartes was telling us back in the day is that if your polynomial has real coefficients, the number of positive real roots is either equal to the number of sign changes or less than by an even number. The number of negative real roots is either equal to the number of sign changes when you put in negative x, or is less than that by an even number. In both cases, count multiple roots according to their multiplicity. Okay, so when we are testing to see how many real roots we have, let's see what that looks like here. So the number of positive real roots, I'm going to start here, positive real roots. I was positive 2 to negative 1, to negative 1, that's one sign change. Negative 1 to positive 3 is another. Positive 3 to negative 1 is another. So I have 3 sign changes. So I can, with 3 sign changes, you can say that you either have 3 roots or less than by an even number. So what is 3 minus 2? 1. Positive roots. So I either have 3 or 1 positive real roots. So now we're going to test for the negative one. So we're going to go p of negative x equals, we're going to take out x and put in negative x. And when we do, we get anything to an even power is going to give you a positive, because you're multiplying negative times a negative, which is positive, and then another negative times a negative, which is positive. So if you have an even even power, then you can say that this is just equal to 2x to the fourth positive. When you have an odd power, because this is negative x times negative x times negative x. So I have a negative and a negative, which would give me a positive, times another negative, which gives you a negative. So it would be negative x cubed. Anything squared is positive, doesn't change the sign, 0. Okay, so we have when we look at sign changes for our negative real roots, we're going to go positive 2 to negative 1 is 1. Negative 1 to positive is 1. Positive to negative is 1. So we are going to have number of sign changes or less than that by an even number. So we're either going to have 3 or 1 negative real roots. All right, so when we look at the graph of our function, we see that I have one negative root, check, and one positive root, check. So Descartes' rules, they give you an approximation, a guess, but you have to actually dive in, verify, look. But Descartes' rule gives you a way to check that what you're doing is right. All right, that's it for this lesson. Go ahead and write your summary. Thank you so much.